Thank you very much. Thank you for giving me this opportunity to be back to the GGI and Firenze again. So what I will be talking about is indeed the emergence of hydrodynamics in the context mostly of kinetic theory, even though what triggered my interest in this game was the notion of attractor, which emerged from holography and strong coupling techniques, on which I will have very little to say, in fact, today, unless there are questions. But mostly what I will be reporting is based on the work that I started with Li Yan several years ago, and the last paper we wrote together is this one. And there is also some extension to, I mean, these papers were mostly devoted to situation with a massless particle and conformal symmetric systems. Whereas with Sunil, who is here in this room, we extended it to the massive case. There is also extension to spin hydrodynamics, which I carried out recently with Nora Wegenant, but I'm not going to report about that. Okay, so what is hydrodynamics? I remind you that there are two basic approach to hydrodynamics. The conventional view, which is based on the notion of local equilibrium, and with the usual pictures, which is a textbook pictures that what happened in the system when you have collisions, for instance, is that the microscopic degrees of freedom quickly reach some form of equilibrium, and the global variables, which are associated mostly to conservation laws, relax on much longer time scale. So that's a traditional picture, which I will basically refer to when I refer to hydrodynamics. And then the modern perspective is based on another view that hydrodynamics should be considered as an effective theory for long wavelength modes. Of course, there is no contradiction between the two pictures, although I want to emphasize that there is nevertheless a semantic twist here. Even though these statements look innocent, it somehow leads to the situation where we may call hydrodynamics things which have very little to do with hydrodynamics in this first interpretation. And we will say that, I mean, this is part of the message that I will be trying to deliver today. Okay, so what happens when the system try to reach equilibrium? There are two things which will be, I mean, they are not independent phenomena, but I'm going to focus on one of them. When particle, I mean, again, I'm thinking in terms of kinetic theory. When particles collide, there is, of course, an exchange of momenta and energy in the collision. And that leads to two things. First of all, there is the population of different momentum states changes and evolve and reach eventually the familiar distribution Maxwell or Bose-Einstein or Fermi-Dirac. And at the same time, there is, due to collision, there is a randomization of the momentum orientation. And that leads to a symmetry, a spherical symmetry of the momentum distribution. And this is the process on which I will focus in the rest of these talks. I mean, I'm not implying that there are specific time scale associated with each of these processes. They usually proceed together. But to simplify the discussion, I will focus on the isotropization of the momentum distribution in this talk and forget about the specific form of the distribution at late time. And you will see that in a moment. That will be a major simplification in the description I'm going to achieve. So the question I'm asking is extremely simple, but it's so simple, it can get a very precise answer, and I hope that will be inspiring for some of you here. So what happened to the momentum distribution in an expanding system? What I claim, as this is well known, is that the fast expansion of the matter, which is produced in, let's say, in a heavy ion collision, as a consequence, to make the momentum distribution flat in the direction of the expansion, simply because the particles which carry a lot of momentum in the z direction, this is a collision axis, if you wish, they will leave the collision zone. And therefore, if you look at the particle, let's say in the central at z equal to 0, after a while, you will see particles which have momentum in px, py, but essentially zero momentum in the z direction. And that can be formalized in terms of different pressures. The pressure is the average of the velocity times the momentum in the z direction. This is a longitudinal pressure, and the same in the transverse direction. So if the momentum distribution is not isotropic, these two quantities will be, in general, different, and that can be taken as a measure of the anisotropy of the momentum distribution. And the statement which is made here is that this anisotropy is somewhat like conservation laws. It relaxes very slowly, like variables which are associated to conservation of energy and momentum. And we want to understand why, and more precisely, we want to understand the competition between the collision, which drive the momentum distribution, as I've argued a minute ago, towards the spherical distribution, and the expansion, which has this effect of flattening the momentum distribution in the direction of the expansion. So in order to do that, I'm going to use a very simple kinetic equation, which has been used by many people over the last decade or so. I mean, it's been used many years ago. It's a simple kinetic equation which describes the evolution of a momentum distribution in a situation where only the direction of the expansion is relevant. So I'm assuming that this distribution function f here is a function of momentum. It depends on the z coordinate, but it doesn't, and the proper time. I'm sorry, this is a typo. It's not meant to be a function just of p or of a t. This is nonsense. But so this operator here describes the expansion with a characteristic 1 over tau here, tau being the proper time. And on the right-hand side, what is written is a model for the collision integral that you would have in a Boltzmann equation. It's written in a relaxation form. This term here will try to drive the momentum distribution at a given time into the equilibrium distribution, which is a function of a local temperature, say, or eventually local chemical potential, but I will consider only temperature at this point. Okay, so this equation does what I want to do. That is to say, it describes the transition from the collisionless regime. The collisionless regime is achieved when you let tau sub r, the collision time, go to infinity. Collision time is so large that no collision takes place, and this term can be neglected. This I will refer to as a collisionless regime or free streaming regime. Particles move on straight line trajectories without being deflected or whatever. And so there is a transition from this collisionless regime to the regime where tau sub r becomes very small. So the particles make many collisions, and this term becomes dominant. And this is a regime which eventually we can associate with hydrodynamics. So this equation can be solved and has been solved, I mean, first time by Gordon Bain in the late 80s, I believe. And it can be done by it can be solved by standard techniques for actually many different forms of tau sub r. In most of what I'm going to discuss, tau sub r will be taken as a constant. But I don't want to solve it numerically. I want to analyze this equation in order to get some analytic insight into what's going on. Okay, so to do so, I am going to use moments, specific moment of the momentum distribution. And as I was saying before, I'm not so much interested in the form of f of p, modulus of p. So I'm going to normalize all the moment with p squared. This is a four-dimensional integral. So this is essentially, if I take n equal to 0, this is the energy density. And all the moments will have the same dimension, that of energy density or the energy momentum tensor. In contrast with what is done most often, where the moments, and if you want to solve the kinetic equation in terms of moments and get the exact solution for the distribution function, you have to work with a more complicated set of moments. So there is kind of a coarse graining which is done here. The reason being is that we are mostly interested in the angular dependence of the momentum distribution and not about, as I said before, about the rearrangement of different momentum shell in the process due to collisions. So this P2n is a Legendre polynomial. For some reason, we call this moment Ln, and pay attention to the fact that Ln refers to the moment P2n. So L0 will be spherical, of course, but L1 will refer to quadrupole deformation of the momentum distribution. There are no odd moments in the system because I'm going to consider a system which is parity invariant. So why moments? Well, I said there are too much information in the distribution function. I mean, if you think of applying this technology to explain experimental data, you have to ask yourself, I mean, can I prepare a system with a given momentum distribution? And obviously, the answer is no. There is no way you can put into your description a very detailed information about the momentum distribution. So it's quite natural that to get rid of some information. And it's not only to simplify the description, but it's also because in practice, it's impossible to handle such detailed information. And as I say, we want to focus on the angular degrees of freedom. So now these moments, the first two of them are very simple interpretation. L0, I mean, the T mu nu is given by this expression here. L0 is equal to the energy density. And L1 is just the difference between the longitudinal and the transverse pressure. You can easily work it out from this definition here. And what we are after is an effective theory for T mu nu, which boils down to an effective theory for L0, L1. These are the only two components in the energy momentum tensor in this particular setting, where I assume Bjorken symmetry of the flow. Okay, so now that you have moments, you can rewrite, it's a straightforward exercise, you can rewrite this equation in terms of those moments. And this is what you get. You get an equation for L0. L0 is a little bit special, there are only two terms. L0 couples to L0, to itself, and to L1. And then for a general moment, Ln, you have a term which is proportional to 1 over tau time couplings between nearest neighbors. So Ln couples to n plus 1 and n minus 1. And then there is a term which is Ln over tau sub r. Now, this coefficient an, bn, cn, they are pure numbers. They can be calculated. The first one are important. A0 is 4/3, C0 is 2/3. And these are coefficients which are not negotiable. You will understand the meaning of that statement a little bit later. So this is a system of coupled linear equations with nearest neighbors coupling, as I mentioned. The reason why there is an infinite tower of moment is coming from the specific form of this operator here. So what I'm doing here is making this operator looking very complicated, as infinite towers of moments. However, the effect of the collision is extremely simple and transparent in this writing, because what the collision are doing here is damping the moment of higher orders, except for L0, with a rate which is just given by this parameter tau sub r. So the effect of collision, you see, if there were no expansion, will be to drive all the higher moment to 0. And this is what we expect from collision. We expect, as I was saying before, we expect collision to randomize the momentum of the particles and drive the momentum distribution to a spherical shape. Now, this exponential decay will be modified by the presence of the expansion in a way which we will discuss a little bit later. Now, if we solve these equations, let's say this is one way to solve the kinetic equation that I was writing before. If you take 10 or 20 moments, you get essentially the exact solution. But you will not be able to, so you will get the value of the energy momentum tensor exactly, but you will not be able, of course, to reconstruct the full momentum distribution, which I have argued I don't really care, because there's no way I can say anything about the general form of the details of the momentum distribution. Okay, so now we have so we had a simple equation, and now we have an infinite tower of moment equation. And of course, this is where the concept of effective theory comes in. Moments are useful if you can truncate this hierarchy. If you cannot, you don't gain too much. And I'm going to show you a very simple truncation, which a priori looks completely unreasonable, but you will see that it essentially, with a slight arrangement, leads essentially to the exact solution. So this truncation consists in just ignoring all moment except that L0, L1. Remember, we want an effective theory for L0, L1. So let's write the first two equations and drop the term which couple L1 to L2. Remember, in this game, moments talk to the neighbors. So L0 and L1 talk together. And in fact, there are coupling which are essential for the physics that we want to describe. But L1 talks to L2, L2 talks to L3, et cetera, et cetera. So I'm just truncating here, ignoring the term which will involve L2. I will show you, don't worry, I will show you very, very soon what to do with L2. But for the moment, I just consider this truncation. Now, even though this is not visible because these equations are equivalent to hydrodynamic equation, you are not used to write hydrodynamic equation in this form, but this is the energy density. Remember, these are the pressure differences. And all second order viscous hydrodynamic in this particular context of Birken flow, a la Israel Stewart, can be written in this particular form. So it views hydrodynamics as a coupled mode problem, and you will see that there's quite interesting structures that will emerge from that. One thing which I don't have time and don't intend to is to discuss the mathematics of this problem. It's actually an amazing playground if you want to apply techniques of asymptotic series. You will, I will mention the notion of attractor. This can be used to study the gradient expansion, the trans series, the resummation. You can find an analytic solution of this, and so this is an endless source of mathematical game. And in fact, you can easily get distracted by this because this is rather beautiful. But this is not what I want to talk about today. So the important points that I want to make is that this simple set of couple equation, they captures the most important features of more sophisticated approach, and it can be made quantitatively accurate with a simple renormalization of a second order transport coefficient A1. You see, there are coefficients here, A0, C0, C1, A1, B1. I mentioned that A0 and C0 are not negotiable. They are just coming from basic conservation laws of energy and momentum. B1, as you will see, is associated to the late time behavior of the system. So it's somehow connected to the viscosity. So you may play with it, but we won't. And A1 is a second order, plays a role in this particular game of a second order transport coefficient. And it can be actually modified. And you will, what I will do in the next few minutes is indicate to you how a simple renormalization process fixes the value of A1 in such a way that one is able to take into account the effect of the complete tower of moments. Yes. Yes. Yes, it is massless, yes. Massive doesn't change dramatically the picture, except that it makes life much more complicated. Yeah. But it doesn't change any fundamental aspects.
Yeah, so I was wondering, because here I see that the equation is basically linear in euro and one.
Yes, yes. Yes.
And I have the impression, if we want this even to reproduce the ideal fluid, imagine that, I don't know, the relaxation time is very short. I would need to know the equation of state, which in general, E will be a nonlinear function of epsilon. So my question is, does it happen to be linear because it's massless, or would it remain linear because it's massless? Non-linear.
Well, there would be non-linearity, but not of the type. There will be non-linearity because of self-consistency type of things. But here I've used explicitly the fact that the trace of T mu nu is 0, because I have kept only the two components of the energy momentum tensor, which is energy density and the pressure difference between longitudinal transverse. Okay, so if there is a mass, yes, it doesn't change, but it is more complicated. So and if you want to have details, you have Sunil here, who has suffered on the massive case for quite some time. Yeah. You may, if you say this is exactly Israel steward, I would not disagree. I'm not too sure what one calls Israel steward. There are slight variation from, but indeed, second order hydro. When I say ala Israel steward, it may be exactly what you call Israel steward. You will see more of that. I will try to. I'm sorry. For, yeah. But this is partly what I will conclude. And in fact, this is echoing the remark I was making earlier, that depending on what you do, what hydrodynamics means can vary. But formally, I completely agree. The reasons why I put ala Israel steward is that sometimes in Israel steward you may want to have another relaxation time that a single torsor bar, right? Also in this particular context there is no room for that. Yeah. Absolutely. Okay, let's agree on that. This is not really. The point is that this. At that level, there is no reference to hydrodynamics. It is just a truncation of moment equation of a kinetic equation. Okay. Okay. Well, okay. Let's come back to this because I think there is an additional aspect in Israel's keyword, which may be contained implicitly in what you say, but I'm not 100% sure. So let's leave that for the moment as it is, and we'll come back to it. Okay. So now why is that a good approximation? So now I need to go into some more detail of this equation and in the way we solve them. And in order to do that, these are two coupled first order in time differential equation, which I can rewrite as a differential equation, a nonlinear differential equation for a quantity which is a logarithmic derivative of the energy density with respect to time. So this G0 here is defined by this. Okay, and now, so if you wish, the motivation for that is the following. We expect these quantities, I mean, the thermodynamic variables like the energy density or the pressures, to evolve as power laws at late time. It's a non-trivial thing because remember, I argue that part of the moments, I mean, some of the moments were decaying exponentially, but it turned out that if we take the expansion into account, this becomes power laws. So we expect power laws at late time, and if you wish, this G0 will go to a constant at late time, and that constant will be the exponent in the power law. Now, more physically, you can also connect this G0 to the difference in the pressure, PL minus PT divided by the energy density, and that is given by this coefficient here is 0, C0, and the G0. So G0, you can think of it as measuring the pressure and isotropy in the system. Now, we can rewrite the equation. This is not quite the full equation. This is just the collisionless part. You can rewrite for the two moments here. Okay, maybe I can. You can rewrite you can drop this term, and this is what this equation is. So this is an equation for G0 in the collisionless regime. And here I have added in parentheses the contribution of L2. So in other words, this equation here is exact. Okay? So now let us solve the equation by ignoring this L2 here. So this is like a renormalization group equation. So you have, hence the notation that I've been using. So it's a DG, it's a beta G. Yes, okay. Been too much RG in my life, but so this is a beta function, if you wish. So it's an inverted parabola, and you immediately see that there are 2 points where, the red curve represents this parabola here. So there are 2 points where the beta function vanishes, which means that there are 2 points which corresponds to fixed point of the equation. It's not very difficult to see that this fixed point is stable. This one is unstable. And what is remarkable in that system of equation is that if you look at the equation for the moments and try to consider moments of higher and higher order, which you can do numerically very easily, you will always find the same structure. In other words, in terms of if you solve the moment equation, not in terms of G, but the moment equation will have in general solution. It's an eigenvalue problem, so you can diagonalize the matrix, solve for the eigenmodes with a collection of moments, not only L0, L1, but L0, L1, L2, L3, etc., etc. You will always find the same structure inverted parabola for the beta function. The mode will appear as damp mode, but there will be the eigenvalues will come in pairs of complex conjugate eigenvalues, and there will be always two real eigenvalues, which corresponds to these two fixed points. Now, this is something I do not have a very good interpretation for, but this is a fact. Okay, so now you see this structure being very stable means that the dynamics of the collisionless regime will be dominated by these two fixed points. And in particular, much of the physics will depend on what is going on in the vicinity of a stable fixed point. Now, what is simple here is that in the vicinity of this fixed point, we know exactly the ratio L2 over L0. Okay? This is because in the vicinity of that particular fixed point, the moment decay has simple power laws. It's 1 over tau, essentially. So the ratio L2 over L0 is given by a number. It's a pure number given by the dynamics of the expansion, which is turned out to be 3 over 8. Now, this fixed point here, obtained by solving the 2x2 problem, occur at this particular value, 0.929 minus, or -221 for the unstable one. Whereas we know that if we were solving the exact problem with infinite set of moments, we would get -1 here and -2 here. Now, what I will do is exploit the fact that this fixed point is at -9.29, is not very far from the exact fixed point, which is given by this dotted blue line here. And therefore, if I do that, I can easily, I mean, by plotting this value here, I get the dashed blue line here, which just goes through the exact fixed point, -1. So you see, the fact that this structure is stable allows me to do something which is quite simple. It's take this into account because we are interested in the evolution near this stable fixed point. We know the value L2 over L0, and that allows me to get the fixed points exactly at the right place. Yeah. Yeah. Or you can, this can be obtained directly from the kinetic equation, which you can solve and look for moments, their asymptotic value as a function of time. That is something you can do. And you will discover that the behavior of all the moments, I don't remember, I think it's 1 over tau, they all decay in the same rate. Okay, so remember the fixed point is a fixed point in a quantity which is a logarithmic derivative of the moment. So this, we are interested in the power law. And what I'm saying is that near this, at late time, if you let the system free stream, all the moments will behave in the same way. So that can be done exactly. You can also solve numerically. You can, and you can look at this curve here and do the replacement and find that you get exactly -1. Yeah, remember, these fixed points correspond to the eigenvalues of the 2x2 problem. If you extend in moments, you will find the exact solution and they converge. Actually, they converge to that value, but extremely slowly. That is what makes surprising the fact that we can use such a truncation, because the moment expansion is a convergent expansion, but the convergence rate is extremely slow. Okay. Yeah, there is a tau of a tau sub r here, yes.
So
of course, of course.
But you said that you made a calculation asymptotically at the early times. So would these fixed points?
I will discuss. I mean, for the moment, I have discussed a case where I drop this term altogether, right? So I'm giving you a different view of something which is the trivial solution of the collisionless regime, which you know, of course, you don't have to work too hard to find the solution of this equation here. This is just a function of x minus vt, right? Or z minus vt. So that you know analytically. And from that, actually, you can calculate the moment and find, I mean, this is, so I mean, I'm looking in a rather sophisticated view, I mean, way to something which is extremely simple. Okay, but this is because it will allow me to discuss the collision term in a more, in an easier way. I mean, I should perhaps tell you that we did not get there by pure thought. I mean, a lot of trial and errors involved in the process. Yes. Well, the higher moment have the same dimension as T mu nu, but they involve more complicated distortion of the momentum distribution. So L1 is a quadruple distortion, right? The momentum distribution ellipsoidal shape. Now L4 will be, no, L3 will be P3, no, P6. Okay, so you can imagine in your head the momentum distribution has a more sophisticated form. So basically, what we're trying to say is that we don't really care about this very complicated distortion of the momentum distribution. What happens, I mean, all these modes with very complex angular structure can be resummed. In fact, this is what I'm doing, and in a very straightforward way. Okay. Okay. Okay, so enough for the fixed points. And now this was a collisionless regime where tau sub r is infinite. So now I want to come to the effect of the collision. So when there are collision, the beta function is no longer a beta function stricto sensu. It becomes on W, W being the ratio tau over tau sub r. So this is a form of this function, which is a derivative of G0 with respect to time. Remember this term here, but you see, I mean, this equation, in fact, by the way, yes, this is something that was well known. I mean, it's a rewriting an equation which was used by Michel Heller and Michel Spaniski here in 2015, and which was a great source of inspiration for us. So we were trying to understand in our ways what was going on. So this beta becomes now dependent on W, but there is some adiabaticity going on here, which I don't have too much time to explain. But the change as a function of W is relatively slow compared to the rest of the dynamics. Anyway, when W is very small compared to 1, meaning that tau sub r is big, or if you wish, the expansion rate is large compared to the collision rate, you recover the free-streaming fixed point. Just put W equals 0 here and here. This is the same equation as we had before. However, when W is much bigger than 1, namely tau sub r becomes very small compared to tau, the collision rate is big compared to the expansion rate, then you see by picking the term proportional to W, you have a G0, you have an A0 here. That tells you that G0 plus A0 is 0, and therefore G0 is minus 4/3, which is 4/3 is the value of A0, which is the hydrodynamic fixed point. So what I'm going to call attractor solution here is not what was introduced in the original papers. Is that particular solution of the problem, which starts from the stable collisionless fixed point at small time. So there is a unique solution. You can start at 0 with at the collisionless fixed point, let the system evolve, and when the collision rate becomes comparable to the expansion rate, there will be a gradual transition towards the other fixed point, which is the hydrodynamic fixed point at that time. And you can show that it's not difficult, that all solution of the problem, depending on initial conditions, will converge to this particular attractor solution. Okay, so let me see how it works in a picture. So this is a form of the function beta G0 and tau, which is the same as the W before, as a function of time. So initially, I start in the vicinity of the collisionless fixed point, which, remember, for the, if I take only a two-moment rotation, this is at minus 0.9 something. Okay, and as time progresses, this fixed point evolve, and eventually you see reaches minus 4/3 in a particular way, which is mathematically a little bit awkward to describe. I mean, this line becomes vertical at this particular point. This is fixed here. So this is what we have as an attractor. And to get a picture which is a little bit more intuitive, so this is what I mean by starting at the free streaming fixed point. You start at this point at minus 0.9 something. Then you evolve. And then when you reach values of W which are about the 1, then you make a transition towards the hydrodynamic fixed point. Now, why do I insist on fixed points rather than attractors? Is that as in RG, typical RG, the vicinity of both fixed points is described by simple physics. The vicinity of that fixed point is described by usual hydrodynamics, Navier-Stokes, gradient expansion, etc. Now, there is a whole game which is based on the structure of trans series, which can reproduce this curve, trying to get information about the evolution of this curve by analyzing coefficient in the trans series. But you see, I mean, here, typically what you get, if you expand, if you try to go backward, you get curves which diverge here like this. And the reason is that if you want to get really information for the approach to equilibrium here, beyond the information which is contained in the local equilibrium or near local equilibrium hydrodynamics, then you need information about this fixed point here. That's kind of obvious in this picture, but it's not so obvious or so much emphasized in the analysis based on trans series, etc. Okay, so now let me try to characterize a little bit more the attractor here. And to do that, I'm going to change to allow this parameter here to depend on time, tau. Okay, this is allowed. I can let the relaxation time depend on the state of the system and depend on time. If I do that, I can use a parameterization, which I guess was also put forward by Michel in one of the paper. Actually, there is a subtlety here. This is loosely speaking correct, but what is plotted here is a tau of a tau sub 1. I mean, this. If you change the value of delta, you have to take care of the dimension. So this is an approximate relation there is a unit fixing which is missing here. But anyway, depending on the value of delta, what you can get is a shape of the curve which can be very rapid or very slow. So slow that nothing will change as a function of time. So you see, this is a curve for a very large delta equal 5. So if you start the system here at small time, this is the fixed point for the collisionless regime. You stay there, okay, and then suddenly you go into the hydro regime. So what I'm trying to say here is that the transition from one regime to the other is not universal. It depends somehow on the type of interaction you have in the system. Delta equal 1 is what I have considered in the previous talk. That corresponds to a constant tau sub r. And you can play with other values. You can decrease the value of delta. And you see there is a value of delta for which things become independent of time. I will come back to that in a minute. And there is this regime here that you see where the behavior of the system is linear, which means that there are logarithmic or power laws. And this I like to associate with what's called in some literature the non-thermal fixed point, namely situation where there is almost perfect compensation between the two effects that I was mentioning, namely the effect of the expansion and the effect of the collision. So you reach a stationary state, the system spends a lot of time without deciding which will win in the competition. And that is generating of power law, which looks like what people call non-thermal fixed point. This is amazing that you can get this kind of behavior in this very simple model. So now let me come back to Gabriel's question about Israel's steward. Yes, the thing I wanted to emphasize is that in Israel's steward typical approach, this is let's say this is the form of the energy momentum tensor with a viscous pressure. The viscous pressure in any order has this form of a viscosity and the gradient, which is 1 over tau. And this is the Navier-Stokes equation. And my understanding of Israel's steward is that Israel's steward added a contribution to this viscous pressure in order to force pi to reach the Navier-Stokes value over sometimes tau sub pi. And here is a table of coefficient which enter the 2x2 problem, depending on which kind of hydrodynamics one is referring to. And yeah, so I don't know what to answer to you. This coefficient, you certainly agree that they can vary depending on which realization of Israel's steward we have in mind, right? Okay, very good. So this is all I had in mind. That the value of a coefficient actually depends on the implementation. And you have here, this C were introduced by Michel in their first paper based on the holographic description and strong coupling technique. But anyway, there is a whole zoo of calculations which can be mapped into this simple 2x2 problem. And now, yeah. Yeah, kinetic hydro is, hydrokinetics was already used, and well, it's a lack of imagination, perhaps. I don't know whether it deserves a name either, but yeah, remember the number 31 over 15. This is all I want to say. And now I come to a calculation, a very nice calculation that Gabriel and Georgie have been doing years ago. I don't remember exactly. Oh, in 2020. Which was also something very useful to us. They did a calculation, they solved the Boltzmann equation. And correct me, Gabriel, if I misrepresent what you did, but with the constant cross-section. And in that game, the typical relaxation time is 1 over sigma n, as usual, but n in an expanding system goes like 1 over tau. So this quantity here goes like tau. Right? And this is this corresponds to, in the pictures I showed before, this corresponds to the case where tau is just 0, okay? So we expect, indeed, a flat behavior here, a constant, completely constant attractor. Okay, so now the solution is not expressed in terms of moment, but in terms of quantities which are pi, this viscous pressure divided by epsilon plus p, energy density plus pressure. And this is plotted as a function of 1 over W, where 1 over W, W is essentially the time, but here it's more convenient to think of it as a Knudsen number. Knudsen number being the ratio between the microscopic and macroscopic length scale. So small Knudsen number is here, large Knudsen number is here. This is a regime of small mean free pass, of large mean free pass on the right. So what we observe here is that if you solve the same problem, so the red curve here is Gabriel's solution of the Boltzmann equation. And the dashed line here is a Navier-Stokes hydro. So you see, Navier-Stokes works in the regime of small Knudsen number, small mean free pass, as expected. Now, if you do Israel Steward, and now I put Israel Steward with a specific meaning, with a specific value of the coefficient A1, which is often used in this game, of 4/3, then you get the orange curve here. Okay? If you use a two-moment truncation naively, as it comes from the kinetic theory, by dropping the L2, you get a value which is 38/21. Of course, it's the same theory. So you would say, okay, I'm getting closer to the solution. But in fact, you see, we are not really improving hydrodynamics in a regime where it is supposed to work. Most of this regime here for large Knudsen number is actually referring to the collisionless regime. So what we are doing here is not really improving hydrodynamics proper. What we're doing here, going from here to here, and to the black dots, which I will mention in a second, is actually improving the description of a collisionless regime. And to convince you of that, let me tell you how the black dots were calculated. You see there is a value here, 31/15, which is a value I mentioned and asked you to remember. Where is this coming from? This is coming from the contribution of L2/L0 to the equation. You see, if you remember the free streaming equation, we have here this contribution here. So I argue that if you are not too far from the free streaming fixed point, then you can replace this by a number. And this is what I'm doing here. I'm replacing this by a number, which turns out, I mean, these are all numbers which are known. And this is proportional to G0 plus A0. And if you work out the detail, I mean, it's a simple exercise to do, you will find that this substitution amounts to renormalize A1 to A1 prime, which is A1 plus 31 plus this number here, which is known, and this is 31/15. So you see, what I've done here to reproduce the exact solution of the Boltzmann equation is just not try to go beyond Navier-Stokes. Of course, I could have tried to do that. I could improve a little bit the picture, but basically the curve here is entirely controlled by the collisionless fixed point. Now, to convince you that there is not so much more physics in this curve here, I will use a Pullman phenomenologist type of reasoning. I say, okay, this curve I know should go to 1/2 or 1/4 at large Knudsen number. This is exact. And this is what the exact solution of the Boltzmann equation does. And I know the behavior in the vicinity of this point here because this is given by the viscosity. The viscosity is essentially B1. So I do a simple linear interpolation in terms of Knudsen number with essentially one parameter, because I know that when Kn goes to 0, this denominator drops, and I know the exact dependence in this area here. And for large for a large value of Kn, I know the value 1/4. And this is the purple curve here. So you see, if you know the value here, you get a fairly good representation of the physics with just information on the viscosity. Okay, and the asymptotic behavior, which is controlled by a collisionless regime. Okay, so now let's turn to other functions. I mean, that renormalization cures actually all the problems which you have when you do hydro a la Israel-Stewart without implementing the correct value for the collisionless regime. So this is the equation again. If you do a standard calculation, I mean the standard values of 4/3 for Israel-Stewart, you get there, negative PL. If you use the two-moment rotation, we also get negative values, right? But if you correct for the location of the collisionless fixed point, namely if you treat the collisionless regime properly, then you get exactly. I mean, exact kinetics is the black curves, and what we call kinetic hydro is the orange curve. It's perfect agreement. Oh yeah, I'm done. Yeah, okay, yes. Okay, so the conclusion is, yes, it's 2 minutes. So we've used a very simple kinetic equation for block and flow, which has been used by many people to analyze the evolution of the system in terms of specific moment of the distribution function. I remind you that there is a coarse graining here. We are not trying to reproduce a full momentum distribution, but just the essential part, which contribute to the energy momentum tensor. So we get, I mean, by doing this simple truncation, which we get simple set of equation, which captures much of the second order hydrodynamics, Israel-Stewart. So Gabriel wants to say it's identical. In the structure, I completely agree. I have made the collisionless regime a little bit more complicated than it is naturally, but the structure in terms of fixed points was quite insightful. And an aspect which I have not really emphasized very much is the fact that when we put on interaction or collision, there is a kind of underlying adiabaticity which plays a role, and the attractor solution is a smooth curve which interpolates between the two fixed points. And this is what is said here. So yes, I mean, this was somehow a provocative statement about terminology hydrodynamic attractor. I think I prefer to think of it as fixed point because of the reason I've mentioned, that really to describe what is going on along the curve in the transition region, you don't need only information about hydro, you need information about the collisionless regime. And in that context, hydrodynamics in the traditional way emerges when it is supposed to do, that is to say when the collision rate in kinetic theory is comparable to the expansion rate. And as I was arguing at the end, by improving the transition region, we do not improve hydrodynamics in this conventional sense of the word, but we just do justice to the collisionless fixed point. And as I mentioned in an answer to question, this can be extended to the massive case. Okay, thank you. I'm sorry.
Complex tower to more complex tower depending on momentum, or from 1 + 1 to 3 + 1. What is the effect on the number?
Oh, No, I think this particular structure is very specific to the expanding case, a one-dimensional expansion in a Bjorken setting. I am not sure if you have a more complicated system, whether that structure will survive. We are actually working on extending this to 3+1 or 2+1, but the transverse direction, let's say, if you think of heavy ion collision, the transverse direction is completely different from the longitudinal one, and there is no particular fixed point structure in the transverse. You see, there in the transverse, it's much easier for collision to really bring the system closer to hydrodynamics, because there is no mechanism which force the momentum distribution to take a particular shape. Whereas in the longitudinal direction, the expansion is fighting against the collision effects. Well, what we are trying to understand is why, I mean, first of all, yeah, there is a statement in the literature that hydrodynamics works even in regime where it's not supposed to work. And this is the simplest case where you can see that what one calls hydrodynamics, I mean, of course, if you call the whole thing hydrodynamics, it works perfectly, okay? But if you want to extract information from that analysis on the physics of the system you are studying, you have to know what you're talking about, okay? So there is this effective theory for T mu nu, which looks like Israel Stewart, but in a regime where you claim that hydrodynamics works, out of equilibrium, you're not really describing hydrodynamics in the conventional sense of the word. You are describing collisionless regime. And that's important if you want to think about the actual system. What is going on, really? Are the particles colliding a lot of time, making somehow local equilibrium, or are they just flowing? Like you may think of initial parton system in a collision to be free streaming, because collisions are very rare if the partons at the beginning of the evolution. Okay, but this is, was a very simple context in which we could answer precisely this type of question. Okay, we are not claiming that this is a tool to solve hydro in 3+1. Yeah, Renzo. Well, anisotropic hydrodynamics somehow, hides, I mean, how to say that? You see, anisotropic hydrodynamics assumes that at early time, the evolution of the system is given by a certain form of the momentum distribution. And that, if you look into the detail, captures exactly the same information, right? So somehow you may say, okay, in a way, anisotropic hydrodynamic at early time is just capturing the collisionless regime, because this is a dominant form of the momentum distribution at early time. Okay, so I don't think, I mean, in a way, it's a conceptually, there is not much difference, I would say. Okay, but you have to keep in mind that when you are at early time, you are making an ansatz, which is telling you a lot about the form of the momentum distribution. And that has nothing to do with local equilibrium. Okay.
Basically, the Bjorken symmetry, the fact that you have one expansion in one direction, the others. But the question is, are there any other flows that are similar in the sense that they have an expansion only in one direction, but the scaling is not 1 over tau, that this language can still enter?
I don't know. I don't know. I mean, it is a. I mean. Yes, no, I don't know. I don't know, honestly. The 1 over tau is really playing an important role here. You see, I mean, in many ways, because you see, one of the issue, if you want to think in terms of momentum distribution, you see, if you manage to make the momentum distribution isotropic, then you are done, basically, right? Because there is not much you can construct with an isotropic momentum distribution except energy density and maybe a shift of the momentum, which is a current. Now, if you are in Bjorken symmetry, in that context plays an important role because you know before doing any calculation the local rest frame, right? You know the fluid velocity, and if you sit in the slice z equal to 0, the velocity there is exactly what provided. So if you change that, what I mean, if you change that, then you will have to work a lot to bring yourself into the local rest frame and so on and so forth. No, yeah. You see, yes. In fact, no, you're right. In fact, we spent quite some time trying to understand the flow in the context of holographic theories. Okay, and indeed you have things like 1 over tau squared, if I recall correctly, but that did not take us very far for the following reason. In this holographic description, there is no universal early time situation. You see, when you solve the Einstein equation, you have a regime where the system depends very much on the initial condition, right? And so there is nothing like a collisionless regime, and for good reason. If the system is strongly interacting, you don't have this notion, right? So in that particular case, you do see the emergence of hydrodynamics in the sense of small gradients and so on and so forth, but you lose this nice structure of having a place at small time, which is universal. The sensitivity to initial condition, which is too big. Yeah. Yeah. No. No, if you're telling me that what people have in mind, this is not what I understand from many discussions or lectures I followed, that hydrodynamics works in a regime where it's not supposed to work. If you say this particular structure is what I decide to call hydrodynamics, then there is no. This is a semantic twist that I was mentioning at the beginning. Then we don't disagree, absolutely. But you see, you have to recognize, nevertheless, that there is a difference, even in this particular model, which is very simple. There is a difference between the vicinity of what I call the hydrodynamic fixed points and the vicinity of the other fixed points, which describe collisionless particle. So if you say, if you incorporate in what you call hydrodynamics the full solution of the kinetic equation, then there is no disagreement. Yeah. But remember, I mean, I incorporate all the moments. You see, I mean, yeah, this is exact solution. This is essentially, this curve here is essentially the exact solution of the kinetic equation. Exact. This one? Yeah, this one. That's. This is a two choice of a coefficient. Yeah. Of course. Yeah. Navier-Stokes is here. Yes. What do you mean really bad? Yeah, but of course it's bad if you have in mind that some correction to Navier-Stokes will bring this curve down here. But this is not the point. Oh, it will make it better in the vicinity of this point. You will be able, you see, I mean, this matching between the orange and dash is superficial. The real matching should be over there. So there is room for correction to Navier-Stokes. Yeah. Yeah. Mm-hmm.
It breaks down. It should break down.
Yeah.
This is what people usually think I want to do. When you do the sword theory, the moments in the mind, even in the sword theory, which is a little bit far from the points, but it's far by, it's not parametrically far like that. This is the point. It breaks down, but it doesn't completely deviate.
No. Yeah, well, okay, no, we don't disagree. I mean, you may say this is better than Navier-Stokes. This is an improvement. The thing which I'm trying to emphasize is that this improvement has nothing to do with improvement of hydrodynamics in the usual sense of the word hydrodynamics. It's an improvement because you say Israel-Stewart is the right theory, and I can improve. But Israel-Stewart is improving, quote unquote, because Israel-Stewart has a structure such that it captures part of the collisionless regime. So this is my main point. I mean, we don't disagree with the structure of the equation. It's just the interpretation. That's hydrodynamics, improvement of hydrodynamics. I don't see improvement of hydrodynamics from that calculation. Oh, okay, yeah.
Yeah, my question is concerning this code. Suppose that you had a whole master graph, not master.
Okay.
So the question is, how so would you expect this picture to change? So my question comes from the idea that you have Israel-Stewart, you have any kind of arc. Israel-Stewart, you have an equation of state. Among the ingredients of the equation of state for the master class is tricky.
Yep.
And it works either at the equilibrium, out of the equilibrium is always P equals epsilon third. But if you have a master class, equation of state is genuinely thermodynamic. So you have to know the relation between pressure, temperature, and pressure in order to obtain the relation between P and epsilon.
Yes.
Yeah, so the question is, if you So suppose you have a master gas, would you expect this, I guess, either of the two moments to be as good as
We have not compared, as far as I recall, a solution to Boltzmann equation. No. But the same. You can have a different equation of state, in particular, different speed of sound, smaller than one over 3, and that, as I say, it complicates the issue a little bit, but nothing really profound changes. You see, the reason is that the major changes are due to the trivial part of the problem, which is a collisionless regime. Okay, so this can be, I mean, we have worked that out for Boltzmann. We have worked that out for the Boltzmann in the small angle approximation for the collision kernel. And there is not any difference, right? Because what we do is not really worrying about the fine structure of the collisions. Collisions do what they're supposed to do. We are just taking care of the trivial part, which is the collisionless regime, right? And that collisionless regime is moderately affected by the fact that there is a mass or not. I don't know whether Sunil is here wants to add something, but I don't recall making a test with a specific Boltzmann equation. We did test with other Boltzmann equation. I showed the picture from the calculation by Gabriel, but we have in Frankfurt they have solved Boltzmann equation in all possible ways in this 1 + 1. And if they correct for the coefficient of the collisionless regime without painful effort, yeah.
My question was really Professor. So if I understood this point was that this has to capture something of the free spin gradient.
Yes.
Yeah. So, and I was wondering how this statement depends on the fact that you have a master gas. I would expect naively that if you have a master gas, then this either Stewart mimicking or capturing sufficiently collisionless regime would be worse.
I am not sure of that. Yeah.
Yes. First of all, yes, you would have a dynamic also by viscosity. So if scrapping is the only moment beyond the energy, the anisotropic pressure, right? But then if you add that you have a mass, then all of a sudden also the isotropic part of the pressure can go out of equilibrium. So you need an additional moment that in the Israel language would correspond to the light viscous stress.
Yes.
So you would have 1 degree of freedom, right? But the language is similar.
Yeah.
And concerning the discussion about its hydrodynamics versus not hydrodynamics, I think that indeed there is some confusion in the field that needs to be clarified, and this work, I guess, is important. And also the comment of Gabriel is correct. So when you say hydrodynamics works, what we're really meaning is there is a system of partial differential equations for a couple of fields that reproduce the curves, right? But then in the mind of many people, hydrodynamics works means this is a gradient expansion, right? But that's in general not the case. Israel Stewart is not really, I mean, there are methods of arriving at Israel Stewarts from a gradient expansion, but that's not what is happening here. If you start from the naive PRs that has gradient expansion and you compare it with the attractor at other times, you get stuff that is much worse than this in general, because it's the structure of the pi dots of Israel Stewarts that changes the dynamical behavior of the equation.
Yeah.
Yes.
Yes. The coefficient will be very different.
Saying I have pi dot, or maybe I was saying I have a sigma mu dot, right?
Yes.
It is completely the solution at a high grade.
Yeah. No, I agree.
Taking some differential equations that more or less captures the stresses and so on, but it's not the same as saying the gradient expansion.
Yeah, but you see, the important thing is that beyond this semantic issue, which is, I mean, we can debate, and it's not uninteresting. But I think if you want to use this to say something about what is going on in a system, in a physical system, you have to be very clear about what you mean by hydrodynamics. Because this is, it's not the same if you're saying that this is hydrodynamic equation which describes the result, but most of what the fluid is doing is free streaming, or whether this is a regime which is dominated by collision. Then the question of why it works so well becomes a real issue. Okay.